It's our pleasure to introduce Vinay. Vinay has been co-advised by Andrea and myself for remember how long, but it's been a pleasure to have him with us and here for his defense. So he's gonna, if he gave a talk uninterrupted, it would take
45 minutes.
Something like that, he promises. But we have the 2-hour slot. So probably just for simplicity, during the talk, we'll try to just have the committee ask questions. And then if there's time for that, we can do otherwise. So I think let's get going.
Right. Abstraction is both the most powerful and the most dangerous concept in computer science. For centuries, people have built abstractions that ignore some properties of an object so as to focus on the important ones. For example, long ago, racing meant required you to know certain things, such as, does the horse move forward? And is it strong enough to pull me and the chariot along with me? But, new objects are around, and new objects and new trends come, and adapting the old abstractions that we have established for centuries to these new objects loses all the essential information, or this seemingly works, but is this the right way to use this object? So rethinking the abstraction from ground up and adapting the abstraction for modern needs can increase both performance and efficiency. So that's what I'm going to talk about today. Okay, operating pages are a foundational abstraction. Give me 1 second. So they are convenient because they provide isolation. They offer virtualization, demand paging, sharing pages between processes. It was introduced all the way back 6 decades ago in the Atlas supercomputer with Tom Kilburn. And this is Glenn Keller at IBM 360. That IBM 360 democratized or made this the standard of current page sizes. The 4 KB page was first established in this case. And the most interesting photo is on your rightmost. That's UNIVAC 1100. That's the first supercomputer at UW-Madison that introduced paging and virtual memory almost 6 years later, right? History records of UW-Madison from online. Yeah.
Do you know who that is?
No, it's a staff member at DoIT. Yeah. Okay, so clearly OS page is such a foundational abstraction for our field. But this page granularity, though, fixes operating systems' observability and operability. Operating systems are now forced to only observe at page granularity or move things around at this granularity. But as you all know, applications operate at a different granularity altogether. Objects, fields, and records, because you call malloc and new and so on. So this abstraction seems to be leaky because it forces this coarse-grained decisions on fine-grained data. And this semantic gap between application and OS memory model has existed for the last 6 decades. And you might ask, hey, why now? What's changed? So I'm going to talk about 3 important trends that has asked us to re-question or question this again. Go on, Mike.
So because I heard through this talk yesterday, when I read Shelley's paper in 1969 on virtual memory, and I guess the question is this a semantic gap, or is this the fact that pages are too big? Like if pages were 64 bytes, would there still be a semantic gap? Or does it only exist because for efficiency reasons, we want big pages?
Great question. So to repeat, I don't know if you heard, Kim. Should I repeat the questions, Kim? Okay, yeah. So Mike is asking, why is this semantic gap because the page sizes are so big right now? Yes, that's definitely the case where page sizes are big, 4 KB, 2 MB, and 1 GB lately. But even if you had resort to like 512 bytes, let's say, amplification will always exist, right? Irrespective of what fixed granularity page size that you would pick, you might potentially reduce it based on the trends that we're seeing lately. But the the gap between the actual object size that's used versus the size of the page will always remain, irrespective of the page size. Okay, the first trend is storage as we know it is not the same anymore. The storage that we are all familiar with are these devices like SSD and HDD built through transistors connected over PCI Express have this kind of properties where they are block at rest, provide good sequential bandwidth. They really don't, they are symmetric read-write performance, and one or two threads can saturate their bandwidth altogether. But there are new storage devices on the market now, like CXL or 3D Xpoint, right? And these devices have resulted, like people are adopting it and building experiments on it, and they fundamentally have different properties. Like they are byte addressed, they have really good random read bandwidth, and there's this nature of asymmetric read-write performance on them. And funnily enough, they also have the complexity of their concurrency is also is tough because you can have multiple threads operating at different granularities.
When you talk about good random bandwidth, is there still a gap between sequential, let's say, reads that you do versus random reads in terms of like effective?
There is.
What is sort of the ratio?
Right. So it depends on your block size. So if you're doing 256 byte accesses on Intel Optane PMEM, the gap was about 20%, 18 to 20% between sequential and random. That is sequential being better. But as you increase the block size, this gap reduces and shrinks.
Right, so then it's a page.
Yes, that's right.
You make it 4K,
Right. Yeah, that's right.
Okay.
That's right. But comparing this to random bandwidth versus sequential bandwidth on an SSD, the difference is not so much. Right? The disparity is much less. Okay, let's talk about the next trend. As you all might have heard, memory is expensive, right? 50% of server costs today comes out of memory at Microsoft and Meta. And interestingly, the dollar per bit has flatlined for almost the last 10 years due to the end of Moore's law and so on. And thanks to AI and LLMs, DDR5 costs 265% more compared to the last 6 months, right? So memory is not this cheap thing that you can throw at for solving complex problems anymore. And they say every joke has some truth to it, right? And the third trend is actually highlighting that memory remains a constrained resource today in data centers, right? At Google and Alibaba, 65% of memory is allocated, and at Meta, it's even worse. 90 to 95% of memory is actively allocated and used. But interestingly, a lot of this memory ends up being wasted because some examples from Alibaba recently showed that 50% of all accesses use less than 1% of data. Whereas at Meta, less than 3% of data is touched in 24 hours, right? So there is this case of, oh, we want bigger and bigger memory, but looks like we are using less and less of this allocated memory.
That's a good question. Is that 50%, I think it's a number, does that mean any, like, can you infer anything from that? Because it could be half of that would go to the stack. And I would say that's 100% of memory.
Right.
And so I don't, like, I'm just trying to think, like, do I care about that number at all?
Great question. So this particular paper was Hotring, where they studied hash tables, and these hash tables were allocated on the heap, and they studied only the heap accesses. So they checked for these heap accesses, how much of these accesses touch what amount of data.
But even then, it means 50%, it means 50% is going someplace else. And
Right.
again, like 50% is a big number. You know, and so I'm wondering, is that, again, is that a useful metric for anything? I mean, it looks good, but I'm just trying to think, like,
Right.
when I walk out of here, what do I learn differently about systems?
Right. You will learn that most accesses are skewed, and
I mean,
most
like, is
data
that-
is
If you look at LLC cache hit rates,
Right.
you know, this would imply perhaps a reasonably good LLC hit rate or something like that, which is
Right.
not, if you told me some programs have good hit rates, I wouldn't think that was crazy.
that's a great point. The motivation for this paper was that even though there is this hot data which is skewed in small fraction of the allocated memory, this does not fit in LLC. And they have to go through TLB and then keep doing page walks to go to the memory. So this 1% of data at Alibaba seems small, 1%, but this is still large amount of data that does not fit in LLC. So the point of this paper was that, hey, there is some amount of this scattering happening. Okay, so these three trends tells us that we need to go and look back at the semantic gap. So in this thesis, we demonstrate how.
Can I just ask one more question? So you mentioned that a lot of memory is not touched, but
Right.
that doesn't tell me that it could be that all of that 1% lives on one page.
Right.
And then it's great. It's
Right.
just bring in that one page, you throw it all other
Right.
pages, that is fine.
Right.
Do you have any idea what is the granularity of access to data on the page? Because, I mean, it came in the early discussion, like, okay, it's too big, one
Right.
page is too big, whatever. But how big is like the average or like the most commonly accessed amount of data in a page?
That's a great question. And I have data for that, a whole section for that to show you. Okay, so based on these three important trends, in this thesis, we demonstrate how applications memory layout optimization is the key to overcoming leaky abstraction. So there are two ways to doing this, of optimizing layout. One is static layout optimization, where we know the semantic accesses of the application beforehand, so we can say where the objects must be placed and how they must be placed and designed. So that's what we are showing here, where applications was designed to take advantage of this new storage devices, and when we decide dynamically where exactly the objects must be placed in memory. And we demonstrate that by doing so, WiscSort, our approach, can do 3 to 5x better than state-of-the-art approaches. But you'll not always know the semantic accesses beforehand. So for that case, we have the dynamic layout optimization, where we aim to transparently improve memory efficiency of applications for skewed workloads. In this graph, the lower is better. So you're seeing that our solution OBASE does 70% better, like reclaims memory 70% from actual application without any backend, without any tiering or swapping. But when there is state-of-the-art tiering or swapping happening, it does 50% better than that. Okay, here's a quick outline of my talk, where we'll first talk about the static layout optimization that I just spoke about, and then we'll make a case and some studies on this case of the need for dynamic layout, and what are the approaches, and finally, how do we realize this need by implementing a system, and we'll evaluate it and show what are the benefits from it. Okay. A quick overview of WiscSort of this section is we will pick sorting as our data-intensive case study. We'll introduce a new model to represent this byte-addressable storage devices that we saw earlier. We'll show how sorting mechanisms are introduced to comply to this model. And finally, evaluate and show how we are 2 to 7x faster than state-of-the-art approaches. Okay. Sorting, interestingly, at least from this paper from 2022, says 50% of all compute time is still spent on sorting and searching. So sorting is clearly an important application in data centers today. And this paper is from Google. And we are asked, the simple question that we want to ask is, okay, let's take this super important data-intensive application. How do we use this new device called BAS and sort on it? So let's assume we have a key value file in contiguous fashion stored on this byte-addressable storage device. So the one way to treat this new device is, since it has good random read properties or better read latencies from SSDs, can we just use it as slower DRAM? And that's what we attempted. And to our surprise, sorting in place on the byte-addressable storage device directly is 9x slower than sorting it on DRAM, right? Okay, so clearly treating it as DRAM is bad. How about we treat it as a faster disk, because it's clearly faster than a disk, right? So that's where we load the data from the byte-addressable storage device to DRAM and do external merge sort and then write it back. And it was great because external merge sort is now doing much better than this in-place sorting system, right?
Just a question. So you call this byte-addressable storage. Is there anything storagey about your characterization, or is it really worse memory in a way? If you call it WM, because, I mean, it doesn't sound like anything about persistence or durability factors into your models here.
Sure, that's a good marketing.
Since the product is canceled.
They couldn't have done worse.
Okay, so
Wimpy memory, like Bond,
yeah,
Bigger,
right?
bigger.
Big memory.
big memory.
PSM, big slow memory.
Big slow.
For us, we actually treated this as storage when we first saw it because it has persistence. Anything in my mind that's something storage is persistence. You power it off, you power it back on. Is the data still there? That's what storage is. That's how we would distinguish it from memory. And that's what this device offered. So that's why we called it as storage.
Right, but your usage of it and your model are 100% looking at the volatile characteristics of it and 0% persistence character. Like, there's nothing about, like, none of your models about waiting for things to become durable, flushing and
Sure.
things like that. So
Sure.
it's focusing purely on the volatile
Performance.
aspects.
Absolutely. So you're right. So sort benchmark is this famous benchmarking framework where the requirement for sort benchmark is data should start from a persistent device and end at a persistent device. From our perspective, this device fits that model, right? If you are responsible to build the fastest sorting system out there, which starts from a persistent device, this device fits the checkbox, I guess. Right?
So do you actually, just a quick curiosity, do you actually wait at the end of the benchmark for it to become durable? Like, you have a barrier
Right.
there.
Right. So we wait, we finish all the writes, and that's when the timer stops.
But you don't fence and wait for the completion from the memory controller. So it's not actually, small nit here, but you know, when you're pushing this, like, you don't actually wait for the device
Sure.
to acknowledge this is now
Sure.
reached the durability zone.
So we don't do M fence. Yes, we don't do that. That's right.
I mean, it's like,
Few
not gonna
few
make-
nanoseconds. Sure. One way to maybe overcome this is start a time like.
We don't have to go
Yeah,
into
sure.
this.
Okay. Yeah. So clearly, okay, using it as a faster disk is nice, but using it as a faster disk avoids these properties of the device, such as the byte addressability nature of it. So with WiscSort, we show how using all these properties can give you better performance. Okay, so how did we do this? We did this by first modeling the device. Right? What are the important parts of the device that we should care about? Byte addressability, as we've talked about. The sorting goal for that would be to read only the keys because of our setup. Higher random read performance, as we know. So random reads is almost on par with sequential reads. So how about we do random reads of keys and values and bring them only when it's needed? Asymmetric read-write cost, reads can be 4x faster than writes. So we would want to avoid doing a lot of writes to the device itself. And then read-write interference, where read bandwidth can degrade up to 2x with overlapping writes. So we need a new kind of concurrency model where we separate reads and writes, right? Finally, this device also has this device constraint concurrency where certain operations have certain amount of threads to do the operations, while certain operations require fewer or more, right? So one set of pool of threads won't fit. So which means we need to manage read-write concurrency differently. So based on these principles, this model, we designed WiscSort, a high-performance external sorting system for braid devices. And we achieve this through, we achieve braid compliancy through these three different mechanisms: key value separation, interference-aware scheduling, and thread pool controller. I'm going to very quickly go through them. So the first three properties are complied by extending external merge sort and simply saying we'll still have to run and merge phase, but now workloads have we do strided reads of keys and values to generate this index map file as shown here. Where index map file is essentially keys and pointers pointing to the values directly. And we do this because there is evidence to show that keys often are much smaller than the values itself, right? And then this allows us to also reduce the run file write back to the device, so it's complying the asymmetric part. Finally, we also do random reads to gather the values directly to complying with the R part. So there are two variants to this, one pass and merge pass. One pass means because we have fewer data in the memory, you don't need the merge phase at all. You can do one shot sorting of the whole system. Merge pass means you do the whole merge phase. Right? Now, braid, the I and D part means that we need to also control the concurrency. So one common approach in traditional high performance applications is to use a bunch of thread pools to independently do read sorts and writes so that they don't have any synchronization between them, and each of them produce a run file. But clearly, this is not a good approach for this device because there is a lot of reads and writes overlapping, causing penalties, right? So, and also you can't control the amount of reads and writes in this kind of an approach. So a simpler approach is to have dedicated thread pools for reads and writes, and then separate them and schedule them so that they don't overlap. Right? Okay, putting this all together real quickly.
One question. Yeah. The reason people do this is that you get some pipeline effects. Like
Right.
Beautiful.
Right.
The right side figure really gives up pipeline.
Yes.
What is sort of the consequence of that?
Right. That was our initial fear as well. But when we benchmarked this, this approach seemingly was better, even when you overlap compute and I/O. So
Is there a theoretical universe where you could pipeline and control the I/O? I don't know what kind of schedule that looks like.
could be, yeah. So you could have writes and sorts at the same time happening. So which means that you'll now have to do more buffer management. So which means you'll have shorter runs, which means you could potentially have more merge phases as well. So this is a trade-off between how many run files do you want. The more run files you have, the more merge steps that you might have to do later on. So we settled with this because this clearly gave really good results compared to the traditional approach.
Good question. What is the bottleneck here? Like, is there a phase where your resources aren't fully being used? That are getting to sugar on the question. Like, and I can imagine, for example, if writes are slow, that maybe while you're writing, your CPU cores are
Right.
mostly idle because you're in a write phase and you can't do anything else.
Right. This is a great question. So I'll actually come back to these in the lessons learned section later on.
Okay.
That we assume that it's in the system researcher's nature that we need to maximize resource utilization all the time, whatever resource it is, maximize bandwidth utilization, right? But this approach where we are showing that you don't need to maximize some bandwidth if you can just move less data, right? If you can move less data compared to moving more data and maximizing a resource, that would be clearly a better approach.
But I mean, but what that does usually move the bottleneck someplace else, that your bandwidth is no longer the, so I mean,
Sure.
does it, so that still gets the question of what is the bottleneck?
The bottleneck remains, in this setup at least, the bottleneck remains the device bandwidth. So it's the read and the write stages are still slower, of course, than the sorting. But we don't. While each of these phases are happening, we want to maximize those steps, resource utilization. But our goal is not to utilize resource all the time at maximum, right?
I guess the other quick question is, did you think at all what happens if you have multi-tenancy? And so you have multiple people trying to use the opt-in memory at the same time.
Right. We did a study on this in our paper. I don't have that in my backup slides, but we did a study on this in the paper where we have sorting system running, and then we had multiple reader and writer thread applications in parallel that's doing different operations, and how this affects our sorting application performance. Okay, so to quickly recap, right? So we have this unsorted input file. A quick legend: the darker means key, the lighter means value and pointer, but the smaller two sizes means key and pointer. Right? So this is key, this is value, but this is key and this is pointer, the lighter version. So you do a strided reads into an unsorted index map, sort it, write it. You're writing much lesser now. You continue doing this. Read it to a read buffer to the merge phase. And at this step, you do a lot of random reads to gather the values and then write it to a sorted output file. Pretty simple. So let's go over. So we evaluated a lot of these things in detail, like such as what is the WiscSort performance on sort benchmark, which is a commonly used benchmarking tool for sorting. Does WiscSort utilize braid effectively? That's one of the questions that we asked. That we do. Are we using the resources effectively at each step? What is the benefit of these concurrency optimizations and how do competing approaches compare. And also we evaluated different key size and value sizes, and how WiscSort performs for different braid devices, because braid is a model generalizing different devices. So because of with the interest of time, I'm just going to focus on one result, that is, what is the benefit of these concurrency optimizations. So in this graph, the way you would read this is on the x-axis you have different sorting implementations, that's external merge sort and WiscSort, but with different concurrency models. Right? External merge sort with no sync, external merge sort with no I overlap versus I overlap, and so on. So what we're trying to get at here is what properties of this braid model is more important than others for this device, right? So here we can interestingly, so in the external, so okay, so the no sync means that you're overlapping, and then there is interference between read and writes. So which is why in the WiscSort no sync approach, you only see B, A, and R on the top of the graph, which means it's not complying to the I and D properties. Okay. So what's interesting is we observe that the I and D properties are much more important than the B, A, and R properties. So the external merge sort, with just being compliant with the concurrency complexity of this device, is faring much better than a compliant byte-addressable BAR property WiscSort.
Not a sudden thing here, right? The benefits are not that much in the wrong place. It's pretty much the same time. Almost all the wins are getting in this merge phase. You actually use different IO schedules for different phases of the sort.
Great question. So we don't, the principle still remains same, that is to separate the reads and writes and to maximize. So during run phase, it pretty much looks like what you're seeing here, run, sort, and write. But during the merge phase, we collect all the merges. Because doing one random read at a time is pretty bad. So we collect all the random reads that we need to do to a buffer, execute those random reads. Once we fill those buffer, we do a write. But now the pool of write threads is different, because we need to again adapt to the device properties, right? So it still uses the same principles, the same strategies, but it's slightly different from what you're seeing in this figure. So yeah, so this graph is essentially saying being concurrency aware while exploiting byte-addressability and random read performance can also give a lot of benefit. That's the last one, right? So with WiscSort, being aware of all the properties can give a lot of good performance, about 50% performance improvement. Okay, to recap and generalize these learnings from sorting goal to a generic goal is first, byte-addressability means not just read-only keys, but reduce IO amplification. Simple. Higher random reads means avoid redundant reads, where you can design your algorithm to avoid reads that are unnecessary at a given time. Asymmetric read-write means you should trade more reads for fewer writes on this device, and then read-write interference means avoid reads and writes at the same time on this device. Finally, you also need to think about different operations require different concurrency models. So you need to think about how to design your algorithm so you can separate those operations at a given time and provide different concurrencies. Okay, so a quick summary is we showed that conventional access strategies for braid devices are suboptimal, introduced the braid model, and we showed how to comply with this braid model. WiscSort introduced these mechanisms of key value separation, interference-aware scheduling, and thread pool controller to comply with it, and also demonstrated that WiscSort is much, much faster than other state-of-the-art approaches. Now, before I go to the next section, any questions? Okay. So now that, oh, yeah.
I'm just going to say, so you've shown us how to build a braid model for byte-addressable storage devices. And I guess I'm curious about how this result generalizes to new forms of memory technologies. I probably anticipated that this question was going to get asked at some point, but like, how do you distinguish between the characteristics that are important versus the ones that are not so important for determining performance? So like, for example, I mean, I believe that CXL devices are covered under this model, but you could use that as an example. But there are also other new memory technologies that people are talking about in the context of machine learning applications and whatnot. If we wanted to build a similar model for those, how would we go about doing that?
That's a great question. So I have not looked at HBFs, if you're specifically asking about that, but I have looked at other CXL devices. Let me bring up a backup slide for that. Right. So let me present this quickly. So yeah, so I did this when I was writing my thesis. I did the study where, okay, now that we have Optane is gone, what other devices exhibit these properties, right? So I looked at broadly 3 kinds of devices. One is CXL attached DRAM, that's Samsung's CMMD device or Micron's CZ120. They seem to offer the B, R, and D properties effectively, right? So they are byte-addressable, they provide good random read bandwidth, but they also are device constrained because as you have more concurrency, you'll have higher tail latency spikes, and you need to be more cautious about how you schedule threads to do those reads and writes on those devices. So for those devices, if you're doing sorting, then clearly key value separation and thread pool controller and random reads are the mechanisms that we would want to use, right? And so one of the reasons why I also did this was to see, other than braid, are there other properties that we should incorporate into this model for these newer devices? For at least for these 3 devices, it didn't seem so. Go on, Mike.
You get it,
Yeah. So the next device I looked at was CXL DRAM plus SSD, where your DRAM is this cache buffer, and then SSD using SSD as the backend. And this device offers byte addressability to a certain extent, but it's also pretty asymmetric as soon as you fill in your cache, your DRAM cache. And interestingly, in this case, more write reduction seems to be improving performance as well. Finally, the ultra low latency SSDs do not offer this byte addressability nature. It's not an exact match, but I thought, okay, these really fast SSDs, how about them? These seem to offer asymmetry, interestingly, right? So the reads and writes have about 30% difference on these devices. And clearly, in this case, external merge sort is going to be better. Also, if it uses the concurrency complexity, the I property of the model. So for the devices that I looked at, braid seems to be a big umbrella model enough to reason about what are the properties that I should care about. For HBF, I'll have to think about it. I don't know.
Okay, we can come back to that, but thanks for sharing the details of this analysis.
Because my question is on the CXL DRAM SSD hybrid, the case in the middle, it seems like there's this property where if you burst data out, there's a volume you can burst out where all be buffered in memory. But when you exceed that, you're going to start triggering write backs a little slow.
Right.
And that's a uniquely different property of having this write buffer capacity, where if you like write things, you can burst things out, but if you steady state exceed the bandwidth that you can write back to SSD, you're going to get throttled back. And so that will tell you have to sort of, stage your writes in certain burst sizes, or, make sure there's ample time for the write back to happen while you're reading other data or something like that. And that seems like a uniquely different property than any of the braid
properties. Yeah.
This sort of, that it always works, but you hit this clip. It's sort of like garbage collection and SSD, where when you hit garbage collection, suddenly writes get 10 times more expensive.
Right. I guess it's more like, the way I think about this is, it's more like all of these properties apply to the device except until a certain cutoff.
Right, but that seems like a uniquely new property.
Yes.
This
capacity,
this dynamic bandwidth device.
Sure.
The EMEM Optane is like, it's predictable. It's always the same response. It doesn't sort of suddenly switch modes in a way.
Sure.
And this sort of mode switch that you don't know when it's going to happen.
Interesting.
So like a challenge to add.
So I think C capacity is another model.
Yeah. Well, no, what I really wanted
to make it work with the acronym.
When I really remember, but she really wanted B to be C and understand why it's not C. But I really want
break.
I want to break.
Sure. But that's a good point. I should think about HBF with the braid.
This happens because I was talking to Ming about it this morning.
Okay, I see.
Because that was the property he was really interested in.
Interesting. Okay.
Well, it feels like, with your study that you did, you could do maybe slightly more generalized model, even more general
Mhm.
braid, adding this, and then we could re-like them as their empirical, take a whole bunch of different types of
Yeah.
devices. And see how they fit under braid plus whatever. That could be like a fun paper to do. That's not super hard to do, but it'd be
I agree.
interesting.
I agree. I would be interested, definitely, because we could also bring in HBM, we could also bring in HBF, we could also bring in these new devices that people are building for inference engines. So
And it's neat, and still also do it over like grade 4 array.
Yep.
Like the show, like
Yeah.
it's,
yeah.
and then one with like,
Yeah, and I mean, there are also even more exotic ones that, like the folks at Microsoft Research in Cambridge and the Stanford folks, the DAM project, that they have even additional devices that might be interesting to think about.
yeah, nice. That sounds, anyway,
Yeah.
that'd be fun.
Yeah, I should perhaps note this down. Somebody else. Okay, cool. We saw that with the static layout optimization, when we redesign applications, when we know exactly what memory access semantics are, we can design the layout. But that's not always the case. Many databases, key value stores, and we can't determine which objects are going to be frequently accessed and design the layout beforehand, right? And I'm going to make that case in this section now. Why do we need a dynamic layout optimization? Right? So in this is a quick overview. I'm going to talk about a new kind of fragmentation that is pervasive, that is neither external nor internal. And we quantify this hotness fragmentation through a new metric called page utilization. And we show how active pages are mostly cold in both open source and production workloads. And interestingly, object hotness is neither knowable at allocation time nor stable over time. That's something we'll demonstrate as well. Learning from all of this, we'll introduce a need or a concept called address space engineering and how we can potentially reduce hotness fragmentation. Okay. As we all know, object creation order kind of determines their location on the address space. But this is a simplified sentence, but to a certain extent, memory allocators use slab allocation where they put objects of the same size on next to each other as they're created, right? But real world workloads, as we've seen, exhibit this highly skewed access patterns from multiple papers in the past. And there are also multiple papers that kind of from Meta, Twitter, and Alibaba show that these object sizes are also quite small, majority of them less than 1 KB in size. Right? So there is this frequently and infrequently accessed objects intermingled on the same page. So this is the definition of the new kind of fragmentation called hotness fragmentation. Now, how do we quantify this? One way is a simple approach where we say page utilization is the total unique bytes touched divided by the total unique pages accessed times the page size. So for a given time, on the left side, on your left side, so you have this page is demonstrating high page utilization, where you have all the objects in this page being accessed, but the other page is basically low page utilization.
It should be over time window of some kind, otherwise.
Yes, so that's a great question. So page utilization is through over a time window. So it's total unique bytes accessed. This is a simplified version of the formula, but it's essentially total unique bytes accessed divided by total unique pages accessed in a given time t.
Big question is if there's any way, there's a challenge that you can have objects on the page that are freed and aren't allocated. So your utilization could be because of cold objects, which is what you're referring to as hotness perhaps, but it could be that you actually just have unallocated data, which at the hardware level looks like cold, but at the runtime level is unallocated. And isn't cold, it's distinct from cold, like that is a distinct category from cold data. I was wondering if you have any thoughts on how you would measure that as well, because that would tell you, like, could your allocator, if you had a smarter allocator, would it be better? Because if your allocator had less fragmentation, that would solve part of the problem. It wouldn't adjust hotness, but it would adjust the internal fragmentation.
Correct. So some papers have tried this approach, like the Alaska paper, which uses handles to avoid this unallocated fragmentation problem as well, where
my question is just if you have a sense of how much of your hotness fragmentation is due to internal fragmentation.
Yeah.
Or
so
allocated space.
So the allocator's goal is to fill in these holes that are created
Right.
when objects are unallocated in these pages. So every allocator that we worked with, tcmalloc, jmalloc, glibcmalloc, has this goal, right? So any free space, it just allocates it. So most pages that we are dealing with in this heap are allocated because we just load the data, run the experiment. There's no deletions. Some experiments have deletions, but it's mostly loaded data. Right?
Okay.
And the case with deletions and insertions, those holes that are created gets filled up by the allocator. Yeah. Okay, so there's this new metric. Let's study some workloads with this metric. Right? So we studied 3 open source databases like MongoDB, Memcached, Redis, with YCSP, which is a common benchmark that people use. Right? So on the x-axis, you're seeing per page utilization. That's basically saying for each page, how much bytes are utilized or accessed. And on the y-axis, you're seeing a CDF, which means what fraction of pages of all the pages that were touched by this application, not pages that are resident, but all the pages that are touched by this application, utilized what fraction of the page, right? And it was interesting for us to see, even for longer epochs that we studied, the per page utilization pretty much remained the same, and it was pretty low, where 75% of access pages in Redis utilize less than 3% of their capacity. And this was a little better for MongoDB and Memcached, but still 95% of the pages use less than 50% of the page. So this goes back to how objects are spread across on your address space and scattered, and really has this amplification in the page. So okay, this was great for
about that might be just a timeline plot where you kind of show this baby operation over time. Just to see if there's any temporal effects. Does it start out very high and then does it drop to like just the median utilization of the 98%
Right.
utilization and over time?
Right, that's a good point. It's a good point. We don't have a page utilization, we have memory utilization and so on over time series, but this YCSP workload don't change really after the workload starts. Right, so it's going to remain same even if we look at longer time periods. That's what I would guess. Yeah, so open source workloads are bad. What about production workloads? So here we are using Google's public traces to analyze what is the page utilization for 6 different workloads at Google. These workloads are YouTube servers, Gmail, it could be anything, right? We have no public information on those. So on the same thing about x-axis, it's per page utilization of all pages. And on the y-axis, this is CDF of pages, right? And you can see a lot of these pages seems to have 70% of their page capacity seem to be with just cold capacity again. So some of these lines are essentially databases which seem to be somewhat doing better, SQL databases, but some servers seem to be, some serving instances seem to be doing pretty bad, right? Now we wanted to study this further, so we asked, what about page sizes? Is there a difference between 4 KB utilization and a 2 MB utilization? So in the per page utilization of 4 KB, it pretty much remains the same to this graph, indicating that most pages in these workloads are 4 KB pages, right? But when we looked at the 2 MB pages, they're really worse, right? So 90% of huge pages utilize less than 10% of their capacity. Okay, so clearly there is this active pages are mostly cold seems to be pervasive everywhere. So can we perhaps allocate these objects before the application itself starts so that this hotness fragmentation is not so widespread? Oh,
So
sorry.
just a quick clarifying question. So the analysis that you're doing here, is that assuming the page sizes that were used in the traces, or is this imposing a particular page size on the addresses that you've observed in the traces?
Great question. So this is not, we're not making any assumptions here. These are actual data where we know which address falls to what page size. So we collect SMAP data along with these access traces, and then we take the address and then see which map it belongs to in the S map. And we know from that map what the size of that map is. Are they 4 KB or 2 MB?
Suppose if we were smart, we could reverse engineer what fraction of pages Google uses for use cases.
Yeah, no comment. Okay, so, but yes, if we want to reduce this hotness fragmentation, one way is to just put all the hot stuff together. But we wanted to study if this is the case. So we took Meta's KV cache-lib trace and said and looked at what are all the records with the most access counts, and then sorted them on the x-axis by the most accesses on the left side and the least accesses on the right. And on the y-axis, it's essentially logical time. So there is no time in these traces, so they don't give you when exactly a record is accessed. So we had to come up with our own way to create logical time. Right? The way we did this is we just said 10 million ops per bucket. So each pixel is essentially a bucket, or like there are 100 buckets here. And if there was an access in those 10 million ops, then the object will light up. So what we observed is there is bursts of activity followed by idle gaps, especially after certain hot pages. You can see there are transient hot, each line is a record. So there are transient hot objects and then idle time, but that becomes even more eminent. You can see that more well in the right side of the graph. So object hotness is neither knowable or kind of stable over time. This was not an artifact of one trace at Meta. We observed this at multiple traces at Twitter as well, from Twitter's key value traces. Oh, yeah, Kim.
Do you expect that the key value cache behavior is going to be similar to the anonymous page behavior in the virtual memory system? I mean, can we take this knowledge of how key value objects behave and actually apply it to more generally to in-memory contexts?
So the Twitter KV trace is an in-memory workload. The cache-lib trace is a caching approach, a caching workload. So yes, from the in-memory context, it'll be good for us because we OBASE, we focus on optimizing the in-memory layout of an application's memory footprint, not how the layout is on the disk. So yes, so this will definitely help us if it's an in-memory trace. So to give an exact answer, so the Twitter KV trace is an in-memory trace.
But I thought your question was more like, is this KV space too narrow to generalize from too much?
Yeah, that's really my question. I mean, like, the KV space is, lots of people have studied, and there are Zipf-ian distributions that we can apply to KV cache popularity, KV object popularity, and is the same kind of distributional sort of assertion true for virtual memory?
By virtual memory, you mean any other application that's using virtual memory?
I mean things that are not key value caches. So pages that are anonymous pages in memory. They could be any sort of application data.
I see. So can you extend this even to pages? Are pages also transient by nature?
Or are objects that are allocated within pages.
I see.
Transient in the same way.
Got it. I would assume it would be the case, but I don't have any trace to prove it. Right? The only traces that are available publicly are these key value traces. But I would assume it to be the case where even if you have PageRank as an example or BCC as an example, you will have certain nodes that are hot for a period of time when you're traversing it, but after a while there will be certain other nodes that will be hot. So there'll be burst of activity for certain objects, and there'll be burst of activities for certain other objects. So this has been actually shown in many of the recent Turing papers, where they show a page can become hot and then slowly start cooling down, and then again can become hot again. And how do you adapt and promote it and demote it accordingly? So this definitely exists at the page granularity, and we have data for that. But for object granularity, these are the only traces that we can infer this from, that I'm aware of. Thanks. Okay. Okay. So we talked about these different characteristics. Let's quickly talk about what are the rewards of improving this page utilization, right? The first one is increased reclaimable memory, which means you need fewer pages to serve skewed workloads. So in this example here, we are seeing YCSP running Redis. Over time, you can see the red line is the number of cache lines that are touched, the green line is the number of pages that are touched, and the blue line is the total memory footprint of the application. And from the OS perspective, it can reclaim all this part, the blue part, easily because it sees that there's no activity. But it has no idea that there is a big gap between the actual cache lines touched and the actual touched pages, right? And this graph is even more interesting, in my opinion, because this is, again, going back to the 6 traces from Google. On the y-axis, you have percentage. So the gray dot bar indicates what is the total pages accessed relative to resident set size, or the amount of memory that's resident in DRAM right now, right? And we can see Bravo, Whiskey, Yankee has like 90%, 80% utilization of resident memory. And the OS thinks, oh, this is a very hot application. But when we look at the dark bar, the bytes accessed per total RSS, we see only 3%, 2% of data being touched for the entire footprint. And the red bar on the right side is showing what is the total bytes accessed of all the pages that are accessed. So this, again, further reinforces our claim that objects are scattered across your address space, and it creates this notion that there is a lot of memory demand and need, but that's not reality at all.
2 questions here. One, so what is the time frame here?
Great question.
Is this? Yeah.
Great question. So we did experiments until some of these. So not all of these are similar time periods. So we have some traces are up to 30 seconds. Some traces are up to 40 seconds. But
so if you look, like, my question is coming from, like, if you go by that 5-minute rule, you want to keep things in memory that are referenced for 5 minutes. Like, can I learn that from this trace, from this picture, or is this not have great information that granular? We
do not have information at 5 minutes. I mean, we did an experiment. This is not public data. We have not released it publicly, at least, where we ran this trace analysis for 1 hour traces, and we saw similar results. But yeah,
so this
it exists.
The order, like, these are things that are not accessed in a minute.
Yes, this is not. This is
so that are never accessed within that.
Correct. Okay.
Actually, got one other.
Okay. Okay. So there are these rewards that we can. So the increased reclaimable memory is one reward. There are other rewards, but I don't have time to go over them quickly. So I'm going to just talk about them in one box, right? So with being able to increase page utilization and hotness fragmentation, you can target specifically which pages must be promoted to huge pages. In big data center companies, it's common trend that you need to increase huge page footprint or increase the address space's huge page memory. But we are arguing that that's not really the case or a need, because if you know which pages are really, really hot, by making them hot, you just selectively make those huge pages. And this is an extended claim where we say if we know, if we segregate objects better, we can then reclaim more aggressively, because building confidence to these reclamation systems and require fewer machines. Okay, these are all great, the improvements of page utilization, but how do we achieve this, right? And for this, we introduce a concept called address space engineering, where we engineer the application's virtual address space to be OS steering friendly and adapting to the workload's access patterns dynamically over time. So how do we go from this left side part where we have hotness fragmented virtual address space to a hotness organized virtual address space? And there are really 3 key principles in achieving this. 1, decoupling the layout decisions from tiering. 2, dynamically grouping objects by access intensity and activity. And 3, enabling this object mobility in the first place. So in the next section, I'm going to talk about how we realized address space engineering with our system and what are the key components and some evaluation. Any questions? Okay, great. Here's a quick overview of this section. So we'll first talk about the challenges of realizing address space engineering, a compiler runtime system that dynamically reorganizes the virtual address space called OBASE, key components, and we show how OBASE increases memory savings of swapping solutions without sacrificing performance. And also we show how OBASE increases performance of multiple page-based steering solutions. Okay, so for each of these principles, there are different components. I'm going to go through each of these principles and quickly review what components we had to build to realize these principles. The first principle is decoupling layout from tiering. There have been a lot of good work on memory tiering and reclamation, like kswapd, TMO, ZSwap, TPP, ARMS. And we want to be able to take advantage of these tiering systems rather than building yet another competitive tiering mechanism, right? And we want the solution to be adoptable. So we want no new OS abstractions or require hardware knowledge to an extent. So if you had a question.
This is a question I sent you an email, which is what is your compatibility story for applications? Like how much work are you willing to make application developers do to accomplish this?
Right. Right now, if you want to support a data structure in our system, you have to specify which variables of your data structure you want us to manage for you, this management of objects.
Another way, if I have if you're running new code, that's a good answer. But if I have an existing code base like memcached, my question would be, how much work would it be to convert memcached to using OBASE?
Great question. So the current setup looks like this. You don't need to write any new code. You have your C++ source code, whatever code that you've already written. But the user must specify which variables that the OBASE system must manage and reorganize on the address space through a list of saying, okay, these are the variables that I want you to manage. These variables essentially point to an object, and these pointers have unique ownership of those objects. So we have three passes. First, we extract the visibility, that is, which of these, where are these variables and pointers, which public functions, private functions are they part of?
Yes, this is another question. If you say variable list, is this global variable, is this local variable? Like every time I use a local, should I have to identify every function that has a local variable that you have to manage?
Yes.
Okay.
Yes, it's any local variables right now.
Every variable.
Yeah, every variable. So we use so LLVM IR provides really cool tools to do static analysis and to say which pointer is part of which function call and what are the function stack trees and so on. So we use those things to say, okay, first look at all the public and private methods where these variable pointers are responsible for, and then we go and change these variables to a certain type of a pointer that we can manage and organize. And then we'll finally insert certain tags. I'm going to get to all of this eventually, but I'm going to certain tags.
Really, the programmer has to do the first.
Yes.
That's
Yes.
it. Everything else is done.
Yes.
Just to follow up on my question, for a system like memcached, right?
Right.
There is the code base.
Right.
How big is that user specified variable list, you think? Like, is it 10 variables? Is
It's
it
a great
like
question.
100,000? What is the number?
Great question. So for most of our use cases, it was two variables only, because it was key pointer and value pointer.
But was this any existing, this code that you wrote, or is this existing?
Existing. So we took acyclib is implemented 10 or 12 different data structures with different concurrency mechanisms. We took that code base because we didn't want to implement our own highly different concurrency model data structures. So this is from ETH Zurich. So we took that code base and looked at the variables and said, okay, these are what kind of compiler paths that we must write to support and optimize this. So to get back to your exact question on, hey, do you support memcached or Redis? The objective of our project was to see if this is even feasible. Like if you have to move an object in C++ or an unmanaged language, what does it take and how do we do it? And not building a compiler infrastructure to make it a real system that any system can go optimize it for, right? So yeah. Okay, going back to this. So one requirement is decoupling layout from tiering. And the way OBASE fixes this is by saying, hey, how about we have per process user space runtime, and it manages where the objects are through some help with the static analysis and compile time annotations. So this kind of allows us to detach the placement decisions of the pages across multiple tiers that these systems already do versus that the backend does versus the front end, which basically moves objects around. Okay, so the second requirement was grouping objects by access intensity. We all know page table scanning is one way to identify what pages are active. Daemon is another sampling-based approach. Those are great, but those are not helpful for us at all, right? Because we are looking at object granularity. And what do we have for that? We have pin tools that are and memprof. These are really expensive, 30x slowdown. We have PEPs, but the problem with PEPs is that it's again sampling-based, and you don't know exactly which objects are being accessed in that page. But the requirements are essentially tracking. We need to track activity at this allocation granularity, while activity tracking itself must be super low overhead.
You need precise information, like PEBS is sampling.
Correct.
But it seems like for some uses of this, you might want precise information.
Yeah.
So like you guarantee to never miss a reference, which
Correct.
allows you to, so is that a fourth requirement? Is that a fourth requirement or not a requirement?
So our requirement is we should always know that there was a reference happened to an object. So that's why we can't rely on PEBs.
So there is a precision requirement.
Yes, there's a precision requirement for the correctness aspect of moving an object.
Sorry, I have a slightly autonomous question. Maybe you can postpone it later, but if you did this in a managed memory language, what would you change about your design? Would you do the exact same thing? Or?
Great question. The honest answer to this is we started with C++. Because a lot of code bases written, these hyperscalars are C++.
My goal is not.
But-
my goal is
you
defend what you did.
Sure.
Tomorrow I come and tell you I want to do this in Java. Would you go and implement the same thing or you do different thing?
We would use the same principles that we introduced in this. Especially, I write about this where garbage collected languages today can use the principles that we bring from address space engineering to do object reorganization. None of the garbage collection languages today do this. They have aspects of if there is a dead allocation, they'll remove it, they'll free it, but they do not reorganize the address space for activity. So if I'm going to start a new project tomorrow, I might consider the infrastructure that the managed languages already support in order to make life a little easy.
Some things are simpler.
Yes, some things are simplified. Yes, because I'm going to get to that, like how it's hard to manage things here. Okay, so and as we saw in our study, static hints at allocation time is insufficient. There have been certain works which says, let me look at the stack trace and tell whether this allocation must be hot or cold heap and so on. But clearly there are applications where the same hot allocation can become cold eventually, right? So to address this, we introduced something called tag pointers to track activity of a dereference. So every time, so in the compiler pass that I showed you, these managed pointers will now track every time a dereference happens to an object. And just like garbage collector, we have something called object collector, which periodically scans all the managed objects and maintains freshness and groups them to different heaps. It does this by using a custom jemalloc that we implemented, which allows the object collector to hint which heap the object must go to, and also maintains these heaps in a contiguous manner in virtual address space. Interesting, none of the allocators did that today. None of the allocators maintain contiguous virtual address space. We needed this, or we like to have this because it allows us to do batch optimizations of these heaps. We could say, hey, all this hot heap can become a huge page because we know to certain confidence that all the hot objects are going to go there. Or all the cold heap can become mad-v cold, which means if a tiering system or extracting system is going to swap objects, prefer from that cold heap and not from the new or the hot. So all allocations start from the new heap. Okay, so we maintain some metadata in the top of the address. And as the requirement showed that we need to adapt dynamically. So although this cold heap, hot heap, and new heap exists, it doesn't necessarily need to be in a secondary tier. They're all in DRAM, right? And we have a performance proxy called promotion rate, where we measure what fraction of all accesses in a given time window goes to the cold heap, And we try to maintain this target promotion rate, this promotion rate to 1% based on prior studies. So there's this adaptive threshold which decides when is it okay for an object to go from new heap to a cold heap, and we keep changing this threshold over time with a simple linear increase decrease policy to decide, okay, is it time to go to the cold heap or remain in the hot heap. And we also have this hinted mode where when we reach the target promotion rate, we can proactively say, hey, I know this cold heap is definitely cold. It's time to kick this out of memory so that the application's memory footprint is smaller, and push it to SSD or CXL. Okay, the final challenge is enabling object mobility, right? And the kind of background and requirements is unmanaged languages kind of assume object addresses are fixed after allocation, right? And in order to scope this work, we focused on pointer-based data structures, which are persuasive in like caching, databases, web servers, and so on. And the requirement is also that this must be fast but safe in concurrent environments. Right? So you have some sort of a node, a hash table, script list, or whatever. We have keys and values pointing to these allocations and objects. And the way we do this is essentially every time a thread is accessing a particular object, it basically we track how many threads are actively referencing an object at any given time. This is similar to reference counting, but different. Reference counting of an object was more like which threads are owner to me, not actively accessing. But we, on the other hand, are trying to say what threads are actively using me at any given time. So we need this condition in order to say when is it safe to move an object from one location to another. Only when this active thread count is 0, when the object collector is confident to move object from one heap to another. And even then, it uses a optimistic object migration protocol, which basically it tries to migrate an object. It copies it, allocates and copies the data. But then if it sees that there was a reference to this, it just abandons the work and moves on to the next object. Okay, so I'm gonna quickly talk about evaluation.
What are there any known limitations of this, like data structures that don't work or threading styles that don't work?
Good question. Okay. So these are like high-level limitations of our approach right now, not of address space engineering as a concept, but OBASE and our implementation. Right? That it first, demolishes pointer stability altogether. Every time a user has to request something, you can't have a cached entry. You need to do a get or a set. Like you need to go through the API. Second, you need to have unique object ownership where the user implies that this pointer owns this object, just like how you would do it in std unique pointer, right? And
so, I mean, does that mean like a doubly linked list? Does that not work because there's 2 pointers into an object? I'm not familiar with unique pointing.
Yeah, if it's pointing to another node in the doubly linked list, then not. But if the node is pointing to some other object of the actual data, then it'll work. And this approach is also like by design incompatible with pointer arithmetic, right? Because we are saying objects are now moving around all the time and dancing. So really, there's no such thing as, oh, let me go to this offset and then I can find the object anymore, right? And again, the other limitation was that it kind of requires the language to support operator overloading, especially dereferencer overloading, so that I can track all the objects at any given time. Yeah, this is, I would say, an advantage/disadvantage because some users will say, hey, I don't want you to manage all my objects. I will tell you what to manage, so less overhead. But some might say, now I have to figure out what objects to manage. So, okay. So evaluation. So we pick 10 popular pointer-based data structures, ART, mastery, B-tree, different types of hash tables. They all span across like 6-7 concurrency mechanisms. And we evaluate against 6 different backends from TMO, Memtez, KSWAP-D, TBP, and so on. We evaluated with both YCSB and also production traces from Meta and Twitter. We study the overhead, scalability, and also the adaptive policy on how the cold threshold changes. And we also finally kind of show, hey, if this is all true, if we can consolidate all the applications into a single machine, you can potentially have multiple applications running on the same machine without performance degradation. I'm going to focus on one or two results, depending on time. I don't have a lot. So let's look at front-end effectiveness. Right? So on the x-axis, you're seeing different concurrency models for different data structures, like hash table, Harris, Pug. They span from lock-free to per-node locking to global locking and so on. And we studied YCSP ABC, where we show the y-axis is page utilization improvement without OBASE, right? And we show for all of these workloads, there is up to 2 to 4x improvement. And the reason why you see 2x for workload A is because there is 50% reads and 50% writes. And if you go back and remember our heap diagram, a state diagram, there was new, hot, and cold. So there could be cases where there are new writes in our system, the allocations happen in the new and the hot. So even though we have removed all the cold stuff from these pages, the hot pages themselves are a little far away from each other. So that's why the page utilization itself looks a little smaller, but when we look at the memory reduction, they all seem to be to have similar memory reduction percentage. That's because we are focused more on removing all the cold stuff from your pages rather than really focused on putting all the hot stuff together and packing them together into certain pages. And yeah, so OBASE kind of improves 70%, reduces 70% memory for all of these applications with a menial performance degradation of about 2 to 2.5% throughput degradation and 5% latency, depending on the data structure again, because if you have a data structure like skip lists, which has to go through multiple nodes in order to get to the data, which means you need to do a lot of go through the lot of instrumentation that we have done to get to it. So which means it will be a little more bad in terms of performance overhead. Now let's look at, okay, that's the front-end evaluation. What about back-end validation? Right? Like, let's see how we work with these existing systems out there. And we studied 3 ones. K-swap-D, that's enabled on all Linux, that reclaims under memory pressure. TMO, that proactively reclaims memory. It sizes your C group reduces your C group size every time based on the pressure signals that it gets from the kernel. And then we have C group hot set, where you can specifically say what's the size of your C group, essentially, right? And in this graph, what you're seeing here is throughput and residence size. Higher is better for the bottom, lower is better for the top. And in the no reclaim phase, where there is no front end and OBASE front end, it's pretty much the same. For K-swap-D and TMO, we can see with just K-swap-D, in this case, it uses about 8 GB of memory, 7 GB of memory. But with OBASE, when you have K-swap-D plus OBASE, it reduces memory footprint by 45%. And at the same time, the throughputs really do not change much. And this is because you're reducing the total working set size of your pages because you're putting all the hot stuff together. So fewer pages are really hot right now. Okay, this is great. What about us limiting? If we know beforehand what's the working set size, can we limit the memory footprint? So that's what we did with C group, where we said, hey, we know the working set is really 4 GB of actual objects, so let's limit it. But by doing that, you're reducing the throughput by almost 40% because you now have to go to the disk every time and page in those pages back to memory. So this kind of shows that OBASE achieves maximum memory savings with really no performance degradation in comparison to going to SSD and disk and so on. Okay, a quick summary of OBASE. So there's
quick question before you move on.
Yep.
I'm curious about what would happen if you added the hints to some of the reactive backends.
What would happen if you added hints to a reactive backend, like TMO, I guess?
Like TM, well, or K-swap-D, I guess,
Sure.
And how that would change the results here.
It wouldn't change a lot, because by hint, we are essentially using the kernel's mechanism to move the pages. Because by hint, we are basically saying m advice page out on the cold heap. And by m advice page out, it's the kernel threads, essentially kswap d, moving those pages from memory to SSD. So we are just preempting the task beforehand. So the advantage of having a OBASE hinted version with a good backend would be we'll get to the end state much quicker than without having a front end which is hinted.
And do you expect that that would result in any change to the, like you think that the resident set size and throughput wouldn't necessarily change because we're just getting to the end state faster?
Correct.
Would it potentially impact, say, tail latency and whatnot? Maybe let's follow up about that, after
Okay.
you finish the wrap up.
Sure. Just to finish my thoughts on this, I would expect not so much, because going back to our mechanism, the hinted thing only works when we reach a particular target promotion rate of 1%. Until then, all the objects are still in memory, and moving those objects. And then only when we reach a certain okay state is when we push things down to secondary tier. But yeah, we can get back to this afterwards. Okay, so to summarize, there's a semantic gap between application and OS memory model, and hotness fragmentation, as we have seen, is widespread. Address space engineering is required for improving page utilization and reducing hotness fragmentation. OBASE is a approach to address space engineering, and how we implemented this for pointer-based data structures. But yeah, achieving higher memory savings across diverse data structures is possible if you are okay with a few performance degradation due to instrumentation. But but it also shows how you can improve multiple tiering backends, both reclamation and page-based tiering systems. So this is the end of my outline talk, and I have a conclusion section if you have any questions before that. Okay, sounds good.
That's a very big lead up to
Conclusion.
It's just this is the only important conclusion section. I mean, not really, but sure. Okay, what are the lessons learned throughout my PhD? This is a tough thing to answer, but I don't know. These might seem naive and this is so obvious, but I look back at these and then still feel these are important that I'll take to the rest of my life. That is, modeling the device before redesigning the algorithm is key. Remzi often talks about measure then build. I'm going to extend it to model then build. And going back to this other lesson that moving less data really outweighs moving data faster. Just aiming for maximum throughput utilization is not going to improve your overall application performance. Optimizing data locality and data movement still remains the key. Right? And measuring the problem at the right granularity. There are plenty of amazing work happening on paging, swapping right now, but this was a problem that seemed nobody really addressed in unmanaged languages, even to a certain extent in managed languages, of how to organize and look at the object granularity. And there was no studies out there to say that whether this is a problem. And it was a nice experience to do a lot of these analysis and profiling and so on. Finally, decomposing along information boundaries. And it was also nice to how we decompose the front end and the back end so that we can work with these other existing systems while not really directly competing with them, right? And to conclude, different approaches are required for different regimes, where we have this static-based layout optimization approach with WiscSort when we know this access semantics, but that's not always the case and it's not true. So we'll need dynamic approaches to optimize your virtual address space. And this remains my thesis that layout optimization remains the key for overcoming leaky page abstraction today. Okay, what's next? I will be joining Google. I'll be joining the core ML performance team and moving to California. I'm excited. The LLMs, as you've all experienced and played around with, are really exciting. And this is yet another application for me as a systems researcher to optimize and do well at. So I'm looking forward to that. I'd like to thank my committee members who have constantly supported me through each and every step throughout my PhD and given me invaluable amount of advice. I'd like to thank my lab members. My lab members have taught me many things and created this really nice environment to ask open questions and discuss all sorts of topics. So I'm really thankful for both current lab members and also the past ones, because I've had the pleasure to talk to them quite a bit before as well. I know. I don't know how that happened. This was supposed to be my graduation, and if you remember, right? So like the year when you started.
Yeah.
So, and I'd like to thank my friends from Madison, because people in Madison, these people in Madison made Madison special and made it my second home. And this will be my second home forever. So all the happy moments that I got to share with them, the runs that I went with Mike. Oh my God. Yeah, it says
The name, the CDIS name is.
right. It's
CDIS.
yes, it's CDIS.
Some other thing that it's talking about. So, very fun.
So everybody looks cold other than.
Oh yeah, that's right. I'd like to thank Google, Kim, especially. Google has played a very important role throughout my PhD for the last 3 years. It made me connect with brilliant people and influenced my taste, my interests, and how I view the world. So I'm extremely thankful for that. And finally, I'd like to thank my family, my parents and my sister, and especially my wife, who has been with me for the last 15 years through each step. So thank you for that. That's all I had for today. So if you have any questions, thanks.
Okay, great. How about we ask the committee first for questions if they have any further ones?
I actually only one question. So the beginning of the talk, you made this pitch that the page is the wrong abstraction. You spend the whole talk trying to somehow like patch some leaks and like, try and make like this, whatever the abstractions still kind of work. What is a good future abstraction? So you have this past, present, and future. I don't see any future in the talk. So
right, great. Interesting. So my what I want to convey was that page can remain the future as long as we adopt the abstraction to our modern needs. And so that's what we showed with the second piece of work, that we need to optimize the application's layout so that the page as an abstraction still works. And but in the first piece of work, we showed that you need to abandon pages and do byte accesses whenever possible. So it really depends on your workload to ask yourself, do you know what kind of workload you're working with? Do you know the semantic access pattern before? If you know it, and if you know that abandoning the page abstraction, the block abstraction altogether is a good idea, do it, and you will find success with WiscSort. But if you can't really work around the system which is built for the last 6 decades, see how to optimize your application so that it works well. Adapt your application so that the existing abstractions work well.
So you're saying the alternate abstraction is just use byte-addressable.
Yes, yes.
It's
sure.
addressing.
Yes.
Yes, I don't have any questions, but I want to dispute what you just said. I mean, I think that's what you said. No, which is, I think what you're saying is the problem, the real problem is the abstraction is there are no pages. And so people ignore pages.
Right.
And the answer is that abstraction should be pages. The application runtimes need to be aware of pages, just like C standard library with fwrite and fread know about blocks. And the
Right.
problem is that memory systems are not aware of pages enough.
Yeah.
And that the real answer is page aware memory management as compared to ignoring pages. That seems like it's not a wrong, it's a
Sure.
good abstraction because it's exactly what the OS wants. The problem is the applications are ignoring it.
Yep.
So I thought I'm playing to it completely backwards.
So,
But it's not, you don't have to.
I'm not. I mean, I just want to clarify that I agree with you. If you paid attention to what I was saying, I was like, yes, page abstractions are good, and we need to find ways to optimize the application layout to work with those page abstractions and find it. But Shivram really wanted what is other than paging. So, okay, sure.
Abstractions can become like
Sure.
dangerous things, and they can become like bad things that we hold on to. And we have held on to this page abstraction in 1960. So I'm looking forward to you telling me that for the next 60 years, this is the abstraction that we should go to.
I see.
That's not your claim.
My claim is adapting your application.
Just go ahead and just fly off.
Sure.
What in your abstraction?
Sure. Sure.
Well, following up on that, so I think you've done a good job of kind of separating out the concerns of a front end that's managing objects and a back end that's managing pages. But there is potentially opportunity if we didn't want to have that separation of concerns. And I'm curious about how well you think some of these ideas would work if we were just explicitly managing the objects.
That's a good extension to the question, right? Yes, that's one.
Like in AIFM,
Yeah,
like application
absolutely.
integrated for memory.
Yeah, that's a very good point. That's something that we want to work as in future work, where rather than relying, if we don't live in this world where we want to try to make existing tiering systems good and swapping systems good, let's abandon all the things that have been built, and can we move objects directly to secondary tier and work at this object granularity? Would we need to think about a different abstraction, this object abstraction altogether? Especially, should this tiering system comply with the braid model and understand the properties of the secondary tier, right? That's a great follow-up question to ask, which we have not explored. It'll be amazing to do such kind of a project.
Other questions, Kim?
So refresh my memory on how the remainder of our time is going to be spent. Are we in grilling mode or are we in discussion mode?
Grilling mode, then we will stop, then we'll kick everyone out, and we'll figure out how we're gonna connect with you either by staying on this or calling you on the phone. Then we will deliberate, then we will welcome him back in and give him the answer of our deliberation.
There's no private grilling room.
Yeah, this is just the way we do it is we just ask your questions now or forever, keep your peace.
Forever hold your peace. So I guess one of the questions that I do have is I know a lot of the analysis of OBASE has been done assuming certain things, and I guess I'm kind of curious to talk a little bit more about some of those assumptions. And so, for example, we've looked at memory hierarchies where, say, the DRAM capacity is actually smaller than the next tier down, so the CXL capacity. In practice, that's not how systems are provisioned in production areas. So, performance constraints are like a paramount concern, and not a paramount concern, but one of the main concerns. So oftentimes what you'll see is that the DRAM pool will actually be bigger than a secondary memory tier, like CXL, just to allow the application to have good performance. So I'm curious about how well OBASE would work in those kinds of environments, and whether you think that there would be any changes in the conclusions that you're drawing.
My honest answer to this would be OBASE changes this narrative to begin with, right? But the reasons why we need smaller secondary tier and larger DRAM is because existing tiering systems are not good enough, right? If the existing tiering systems were good enough, then we need smaller DRAM footprint and larger secondary tier, right? But why are they not good enough is because of this hotness fragmentation of where objects you seemingly want more data, right? So in a setup where you have larger DRAM and smaller secondary tier, OBASE is still a good idea because you're still compacting your working set into fewer pages. And deciding whether to move them to secondary tier is up to you, because it might give you more multi-tenancy opportunities. But I think in reality, if more people adopt to being page aware, being the application's memory layout being more page aware, you would get to a point where you don't need to live in this world where you are provisioning more expensive DRAM and smaller secondary tier.
To a point, I would agree with that, but I think there are limits to that as well. I guess another question is around: do you find that there are differences that are required to make OBASE work with byte-addressable backends versus swap-based backends? And even though the same approach might work, do you think that it could work better if you differentiated the type of backend?
Right. That's a great question. If there was a way for the backend to give some information to the frontend, to OBASE, OBASE could potentially use it to make decisions on when is it time to do the reorganization, when is this time, if there is an active, if pages are actively being pushed to secondary tier because of some change in workload, and somehow OBASE knows this from secondary backend, some backend system, OBASE could stop doing it for a while and then stop organizing this whole layout. So if tiering systems could give some info, right now we are living in this detached world where backend gives no information. But if backends can give some information, such as how slow is the actual backend system, what will be the loss of like how slow, I mean, in a sense, would you put a lot more objects into cold heap if you know that the secondary tier is not that slow and it's okay? How aggressive should this target promotion rate be influenced can come from backend.
Yeah, I mean those are other questions that I have, around sensitivity to certain parameters of things like promotion rates, or things like the, sort of the additive increase, multiplicative decrease, or I guess additive increase, additive decrease, kind of approach to, to evolution. But I don't know if we want to get into that level of detail here. Those are that's a handful of questions, and I'll pass the question baton to the next person.
Seems like the OBASE design is really currently designed for 2 tiers of memory, hot and cold. And I was wondering if you have more tiers, if you have, swap and CXL and another NUMA node and your local node, how extensible is it to do that?
Great question. The one obvious extension we'll have to do is have more heaps,
Right.
more designated heaps, rather than saying new, hot, and cold. Have new hot NUMA, hot DRAM, or like new cold NUMA, cold PMAM, or different heaps, which is doable because it's pretty easy, because you just have to initialize these heaps during the start of the runtime, start of the application, which the object collector basically does. And the only drawback I can see with having more heaps and deciding where these heaps is, now we have to do more movement of these objects across different heaps. So there definitely is some trade-off on how many heaps you want and how packed your objects must be. So this is something that we talked about, where it would be nice if it is a spectrum where all the hot objects are sorted on one side and all the cold ones on the other side.
Does that way you're calculating access information give you enough fidelity to distinguish between multiple levels of hotness?
You can tune this. You can say, rather than looking at every 120 seconds, how about you look at every 30 seconds? In the last 30 seconds, have any object seen has been accessed or not? Right? So that will give you the fidelity to distinguish between really hot versus somewhat hot versus cold. But yeah, right now it's just 2 tiers right now.
Yes. So you made the mistake of inviting a machine learning person.
Great.
Because I don't understand 99% of what you said. So I do have questions, like kind of, first of all, I enjoyed this, and sort of like hearing you guys sort of there's two things. There's abstractions that you build, so you can build more stuff on top of your abstractions, and you're able to debug ideas and code and whatnot. And there's also the engineering that goes into that.
Right.
For me, as a machine learning sort of like researcher, the engineering part is always the most annoying and boring aspect of it.
Right.
And why is that? Because it kind of like it's the wall between me and the signal I want to receive from an experiment to see what's the right idea, what's the right hypothesis, and that kind of thing. And so I've been using using agents about 2 weeks, and I've seen, and this is not overhyping, I've seen that they can completely automate all of the engineering that my students used to have to do for setting up sort of like a green type of code base, kind of like starting from scratch, want to run an experiment, test an idea on some model, some data set. All that part used to take a lot of time, perhaps weeks, and now it can be done in an hour with clone code or codecs, right? And so what I'm doing this, so what seems to be mattering now is the engineering had to have some value in terms of the human effort that you need to spend on it. But taste seems to be now what is
important.
It's not, I wouldn't call it the bottleneck, it's like what actually is of value. So like somehow if you have a magic wand where all the engineering work
Stuff
can go away, you're left with what matters, which is basically, the question you ask and the changes you want to make in your code base, your ideas, your abstractions. So I guess my question for you is basically, why in your work did you feel that your intuition and your taste kind of like, took you to the final idea versus sort of like the formalism and the engineering of things?
Interesting. So our lab's motto, I don't know if you've heard, is measure then build. And the reason that comes from basically preaching in front of them, but it comes from measuring a lot of things develops taste, at least for me. So me tinkering around a lot of things. So a lot of this work was done pre-ChatGPT era, right? So a lot of performance debugging, writing really high performance C++ code required me to learn and understand things that I did not know before. If I had asked, hey, Claude, do you think I should do this? It might give me an answer, but I don't know if that's the right answer for me because I have not went and explored around, right? So the same thing, even things like the choices that I've made in the system comes from me reading Hacker News, me reading different things, and then saying, okay, this seems like an interesting idea that I should incorporate in my system. That seems to be lacking if you ask a model to do the engineering part for you, right? And you'll never develop that taste, in my opinion. So I'm just saying, I guess it's just about, it's great as building prototypes when you know what prototype you want to build, but it's not great at telling you what kind of prototype that you can build, or like you can say, oh, show me 4 ideas on how to build this prototype. Sure, it can come up with some 4 ideas, but I don't know. I don't feel satisfied yet on giving all the engineering work to a model. But it's great. I've used it. But for me, the taste that I developed was purely through breaking my head against Optane for 6 months, trying to understand what are the performance characteristics of this device, or optimizing the dereference cost when you're accessing an object so that we are only using like 4 or 3 nanoseconds. I've tried Claude for that. It's not good yet, but I'm sure it'll become better in coming years. And those hands-on doing things helped me develop the taste on what I want to do and what kind of questions I should ask. I don't know if that will change over time, but.
Good. So the second question I have is that basically, you talked about abstractions, and there's many reasons why designing abstraction matters, but also something that's interesting is sort of what's the final consumer of those abstractions. And for many of the things that involve algorithms and systems, humans are sort of like the consumer
Right.
of them, right? So that, you build them so that the design of whatever in the higher abstraction level is easier for the human in the place of whatever engineering job you're thinking about. So as we move kind of like towards the age of agents being faster, being able to produce a lot more code, handling a lot of the low-level engineering, both of the system design, backend, front, this is everything. And this is not, again, I'm certain that for many people this sounds overhyping, but there's companies like OpenAI that basically, and Anthropic, that stopped writing code.
Yeah.
And so
Yeah.
our code is code will basically do everything for you.
Sure.
And now the abstractions matter,
Yeah.
but for a different type of being than the typical consumer of them.
Right.
And therefore, the design of those abstractions will likely change. So if you wanted to facilitate, you know, better, I don't know, yeah. So in a few years, basically, the thing that will operate your system is not going to be human. I think that's the building
Agent.
those abstractions will not be human, right?
Right.
So how does that change what you build, if at all?
How does your abstractions change if it's not for humans? So the most abstractions that we have come up with for computers, at least in systems world, is not for humans, I would say. Page as an abstraction is not really for humans.
They're human design.
The humans are designed it, but it was mostly for the efficiency of the hardware, right? Like when you put all these words together, that becomes a page, and that's good because the hardware that we've designed works well with this abstraction. So even back then, even though humans are designing it, they're designing these abstractions for the hardware, not for somebody else who's using it. But you bring up a very good point about how we talk about, oh, humans are doing this new malloc correctly to optimize the layout of an application on your address space, right? If an agent is doing this, how would that change as an abstraction? Would still use the same abstraction. I don't see, at least in this context, in this stack of systems, I don't see it changing much because we are still modeling things based on the hardware and not modeling things for the user. But if it's an application level, hey, should I change my browser? Definitely should change your browser because agents are going to look at it, not humans. So I don't know if it's a convincing answer.
That was good.
The next one, you even more philosophical.
Sorry, I mean,
Too philosophical.
that's it.
Makes sense. That's it long. It's a great question. So I'm not going to ask any questions. And so think we're good with the committee questions? Okay, and so why don't we have the speaker one more time?